Okay, good morning, everyone. So tomorrow we are having a makeup class. We are starting at 9:30. Room I will let you know. I have actually requested for this room itself, but we don't know whether this will be available or not. So we have talked about, we have been talking about vorticity. And the previous class we looked at how the vorticity appears in the Navier-Stokes equation, which was one of the questions that was asked in the quiz today. And we saw very surprisingly a few things that once you cast the Navier-Stokes equation in vorticity form, I mean, or where vorticity is explicitly appearing. So we saw that it appears, the vorticity appears in the advection equation as well as the viscous terms. So in the advection part, in the advection term, we saw that it is, we essentially generate two terms, whereas when you look at the viscous term, we do have only the viscous, again, the vorticity appearing in there. And it means that if we talk about a flow which is irrotational, then we see that the vorticity, the viscous terms drop off altogether. So that means that an irrotational flow is, for an incompressible case, is necessarily inviscid. Okay, so that is one interesting observation or one interesting comment finding that we had. Then we said that we also got the Bernoulli equation from there. So we saw that, okay, from the momentum equation, it is possible to obtain the Bernoulli equation. It can be obtained not just from the energy equation, which is what a lot of books in thermodynamics and other books will tell you. So it's not a conservation of momentum, or I mean, it's some sort of simplified form of the Navier-Stokes equation, because you can see that a lot of simplifications you have made in the process of obtaining it. And we are normally exposed to only the steady part of the Bernoulli. We saw that it is somewhat like an unsteady Bernoulli which appeared in the equation last time that we wrote it. So that was a set of interesting sort of learnings from there. We also talked about the V times omega Z term, for example, so which appears in the x momentum equation. So we said if we take a vortex which is rotating about the Z axis and we move it along the V direction, there will be a force which will be there in the third direction. So that's the so that's like an interest. I mean, that's an interesting thing that we realized. So any vortex, if we take and we move it perpendicular to itself, the direction of rotation, there will be a force that will be generated in the third direction. Okay, so that's what we learned. Now we had left you with saying that, okay, drive the vorticity equation, and then in the homework we have actually given that as something that you have to go back and drive the vorticity equation for yourself. We are not going to spend time driving that. And I said you can drive it in two different ways. One, by taking the curl of the Navier-Stokes equation, and you can also get by starting off from a form which was given, which was from the previous part where vorticity was explicitly appearing in the Navier-Stokes equation. So you can start off with that form and then convert it using tensor algebra. Okay, and you can have your own observations. And when you do the second part with tensor algebra, you will be needing to use the epsilon delta relation. In fact, epsilon delta relation will make it very, very, very easy or convenient for you to obtain the solution, is what you would see. Okay, so anyway, this is where we had left in the previous class. And again, as I said, vorticity equation, I'm not going to drive here. So what I will do today is continue with our discussion on one is vorticity, some very small things which remain in there, we will complete that. And the second thing that we will do is to go back to our exact solution. We have been trying to drive the exact solution of the Navier-Stokes equation. So we will see essentially two cases, diffusion of, now once you've understood vorticity, hopefully you will be able to appreciate two solutions that we are going to get for exact solutions. One which will be like diffusion of vorticity, and the other one is like the decay of a vortex. Okay, so this is what we will we plan to do that, and if time permits, we will get to the approximations of fluid mechanics. Otherwise, we will come back tomorrow and we will start off with that topic. So, any questions coming from the previous class? Anything from the previous class? Any of the previous classes? Yes. What is the simple thing of circulation? Because circulation, okay, circulation, and we are going to talk more about that. We saw that it is sort of a one parameter which is a measure of the strength. So we said it's like a strength of the vortex. So if you accumulate more vorticity, you will have higher strength vortex. So that's the sort of, so it's a measure of that. So we said that if you are looking at circulation gamma, then gamma is defined as omega dot d area. So this is over an area that is of interest to us. Okay, and we have seen that this is vorticity is nothing but the curl of velocity. Between these two, we have not really done too much other than to use the definition of vorticity and write it as a curl of velocity. But now we are going to use the Stokes theorem, which I am sure you know about it. So it becomes u dot ds over a closed path. So now what it means, and so in the very first part of the lecture today, we will look at how to use this relationship and what it means. So let us say we take a region. We have talked about a vortex tube. So we can think of that there is a region in which I am enclosing a vortex tube. So this is an area. This is the region which is, or this is my vortex core of some size r. All these things are not really important. But what we are trying to say is that if I look at this region and I enclose all the vorticity which is there in that region, then, and we know that this is the only region which has vorticity. Outside that, there is no vorticity. Okay. So then here we are trying to look at what is the total vorticity which is there in my area, which I am enclosing. Okay. And you can see that if I'm looking at this vortex, if I now change the area to this, my circulation will not change, because in this additional region that I have added, so my area has increased, but the region that I have added has no vorticity. Okay, so this omega is not there, and therefore this is not additional. Adding anything additional is not going to help or change anything. Similarly, if I change the shape, let us say I go to a shape like this. This is still a regular shape, but I can go to an irregular shape like this. Okay. So I can go to an irregular shape like this, and the vortex circulation inside is still the same. Okay. So one of the questions that was asked, what is the value of circulation? You can see that now the circulation has importance because it is giving you in that region which is enclosed, what is the, again, what is the, vorticity times the area which is there. Now, why this relationship becomes very important or useful in practice is because I can use one or the other. Because these two relationships are exactly the same. So either we can go with this form or I can go with this form, depending on what is more convenient for me. Okay, so we will take a few examples and just illustrate them. So if I take two vortex tubes, for example, this is one vortex. So one is rotating counterclockwise, the other one is rotating clockwise. let us say they have the same strength. Now I want to find out what is the circulation which is along this path or in this region here. Okay, so I just want to move along some path, okay, and see what is the circulation which is there. What do you expect? Zero. Why? Yes, because they are of opposite direction. So this is plus omega, let us say, and this is minus omega. Okay, and they are occupying the same area. Okay, the same size, same vortex. Is just that, or we have talked about a vortex ring. Okay, in a vortex ring, if I take both the vortices, we know that they are of the same strength. Okay, but and same size, but opposite rotating in opposite directions. And because of the opposite rotation, okay, if we were to find out what is the circulation which is there around this path, okay, we'll find that as 0. So circulation is 0 in this case. So which of these two relationships are we implicitly using? Whether we're using the first relation or the third relation here? The first relationship is what we are using here. Okay, so now let us think of another case, and we will try to see if, so let us say I have a few vortices which are given. Again, this is not a atypical scenario. This could be there. There are some vortices close by. Some they could be rotating in one direction or the other. But then you are given the velocity field. So you know what is u and v. Now you are required to find out what is the circulation around certain path, or which is enclosed because of this. What is the net circulation that I would have? Okay, so then what will I do? Line integral. So u dot ds makes more sense. So what I will do is say A, B, C, D. Now if I use u dot ds, just again remember or understand that u is a vector here, s is a path length which is also a vector. So I can have the same path length, but I can move in different direction. Just like I'm moving, I can move left, right, back, front. Okay, so I can move in different direction, but having the same path length. So this is actually a vector quantity, so which is giving me both magnitude as well as direction. And the dot product between these two quantities is what is implied. So if I want to look at the circulation, so what I will do is essentially u ds over this path, which is essentially equal to an integral from A to B. Path is A, B, C, D, A. So this is an integral from A to B of u dot ds plus integral, same integral over B to C, u dot ds plus u dot ds from C to D plus u dot ds from D to A. Okay, so this is how I'm completing my circuit. And of course, what is important here is that we are talking about an area. Area has to be closed area, otherwise it does not make sense. And if it is a closed area, then that means that there is a boundary around which I can move. Okay, so this is what is implied. So that is why we can convert. I mean, this is always going to be a closed integral. I will have to come back to where I started. If I'm not able to come back, what is, I cannot define circulation. Circulation is meaningless in that case. Okay. So now you can see that I have divided. I'm trying to find out what is my circulation. I know that my velocity field is given to me, so I know what is u and v. Okay. So I can now see that u dot ds. Okay, so this is aligned, let us say, along the x direction. This is my y direction. So my path length is only dx here or delta x here. Okay, and the only velocity component which will matter here is u. Okay, so it's like u times dx integral from along AB plus from here in B and C, I'm moving along this path. So path is along the y direction. So I'm only having the ds is nothing but my delta y. So my dot product will only give me v. So this becomes v times dy from b to c. And then when I go for this path, uds, then I'm going like this. This is my direction of motion. Okay, so from C to D, I'm moving along the minus delta x direction. Of course, if I take a dot product, the only velocity component which will be relevant for me is u. Okay, so it will become a u dx, but with a negative sign from C to D. And then from D to A, it's a minus delta y. Okay, so it's v dy with a minus sign from D to A. Okay, so this is how I can find out the circulation. So you can see that I'm trying to, if I try to find out using this, maybe omega dot dA may not be very convenient because, or trying to have a different path, more circular path, for example, is not going to be that convenient because then my velocity vector and my path length are not aligned. So I have to always take a cos between them. Here, taking a cos for this other case is very straightforward. Okay, so this just illustrates that both these two relationships apply, and you have to just see which one is more convenient to use and use that, pick that, and just work with that. Okay, so this is an interesting illustration of the Stokes theorem, as well as how to calculate, or some discussion on how to calculate vorticity. Okay, any questions here? So just wanted to do this part to make sure that everybody understands or is comfortable with the calculation of circulation. And okay, where does the circulation come into the picture? How is it practically useful? Any one example? To define the strength of an irrotational vortex. Any practical example of where circulation comes in? Yes. Wingtip vortices, and more than that, the practical is lift of an aerofoil. What is the lift of an aerofoil? Rho u gamma, correct? What is the lift force on an aerofoil? You remember? No, you have not seen this formula. Yeah, Kuttajovsky theorem is just sort of says that the separation point will always be at some sharp edges and so on. But the lift that you would get for an aerofoil, so if you look at an aerofoil, there is a flow which is happening around it, and the lift force. Okay, we have not done this, so I'm not expecting you to know, but I thought you would sort of know this from whatever. So from your earlier thing, you have not seen this formula. I think this is one of the very famous formulas, right? So I mean, if you have to calculate what is the lift that this aerofoil would have, okay, this is given as rho u gamma, where gamma is exactly the circulation that we are talking about. Okay, so again, what you will have to do is take a path length. So you can define it by, you can explain it by saying that pressure here is more than, why does the aerofoil generate lift? One can say that, okay, there is higher pressure on this side as compared to the other side, okay, which gives you a net force which is pushing this aerofoil up. Okay, that is one way to think about it. The other way is you just calculate, take a path, a closed path circuit like this, okay, and what you would find is that the velocity along this path, so again you are doing the type of thing that we have just mentioned, okay, and what you will find is that here, I mean, if they were to compensate exactly, so whatever is happening here, if that will compensate on this part, or whatever is happening here compensates along this path, then you can see the one is with a positive sign, the other one is a negative sign, and overall circulation will become 0. But here it is non-zero because you can say that here the velocity is much more as compared to the velocity which is here, okay, which gives you a net circulation, and that net circulation gives you a net lift, okay, from this expression, which you can derive. This is something which can derive from the inviscid theory or potential theory, which we are not going to get into, but one can derive this. Okay, is this clear? Yeah, so one has to, so just like looking at it, one does not know no, how much lift the airfoil is going to have. So I will have to measure the flow field around it. Once I measure the flow field around it, I can use rho u gamma to find out what is the lift that this object would have. The other one, yeah. Okay. So what are you saying here? We do not know how you will carry from A to B. Yeah, so I said that the flow field is given, velocity field is given to you on a Cartesian grid. So UV is given to you at all points, and you find out these vortices are there. Okay, so that's a typical scenario. You do CFD or you do some measurements, maybe a PIV measurement. So then you will find that you have the velocity field U and V, and you will be able to see the vortices by taking the curl of the vorticity, curl of the velocity field. You can find out where the vortices are. Now, if you want to find out what is the total thing, you can of course either use omega dot dA, okay, or you don't even have to look at the vorticity. You just find out what is the circulation. So circulation can be 0 for two reasons, either because there is no vorticity that is enclosing, or there is no net vorticity which is enclosing, which means that we have both positive and negative vorticity, and both of them are exactly cancelling out. Okay, any questions here? So now we had, I mean, you can say that from the cylinder problem, rotating cylinder problem, we took a diversion and we went in for vorticity first because that's a very direct connection that you could see. So it was easy to appreciate, right? So now we can go back to our exact solution, and now we will do exact solution for the cases for which vorticity has been introduced. So hopefully you will have much more appreciation of what we're talking about. So diffusion of a vortex sheet, as it is called. So let us say that we have the following scenario. There is an interface. There is a fluid which is moving in towards the right. There is some fluid which is moving in towards the left. Okay, so this is a scenario that we have at time t is equal to 0. So we have oppositely moving fluids, and there is some interface which is there. Okay, and we would like to see. So you can see, what do we expect to have in this case? We would expect to have large amount of velocity gradients, right? That's very clear that there is a large amount of velocity gradients across this. Of course, initially velocity gradient is infinite. Okay, so you can see that infinite gradients nature may want to suppress that, and we will see what happens. And this sort of a scenario is actually quite common. If you look at flow coming out from a nozzle, this is a nozzle and the flow is coming out. So you can see that at least here, if I look at this interface here, there is the scenario where fluid is moving in very rapidly, outside fluid is having 0 velocity. So here we are looking at u and minus u, but you can think of 0, u and 0, which is sort of representing this case, or you can think of that I am in a frame of reference which is in between the two velocities. Okay. So this is, and we would like to see how this gradient, now this gradient, as we have seen, is associated with both, can lead to both shear, it can also lead to vorticity. So here vorticity is more important or relevant for us. So we will think of it as vorticity, and we would say that, okay, how does this vorticity which is generated at the interface is going to diffuse with time. Okay, so that's the problem statement that we are looking at. Is the problem clear? So let us say that this is my y is equal to 0. This is my y direction, this is my x direction. So what sort of a domain is this now? So we are thinking of that this y extends all the way to infinity, okay, here, and all the way infinity to the other side as well. Okay. So, and what does that allow us? By saying everything is going both the sides, it is infinite. What will allow us to? Gradient is 0, that's boundary condition. But in the method of solving, what will happen? We can look for similarity solution. Okay. So because we're not imposing any length scale, okay, we can look for some similarity solution, and that is what is going to be important or relevant here. So here, maybe to begin with, along the x direction, we know that this is a very large interface along the x direction. So along the x direction, we have already argued so many times that dou u dou x is equal to 0, dou u dou x is equal to 0, and from continuity it means that dou v dou y is equal to 0. Okay, and here it is not very clear why v should become 0 all throughout, but it does become v is equal to 0. Then we have the same arguments going to the y momentum equation, that there is no dp dy, and then we can go to the x momentum equation, and we know that it's an unsteady flow situation. Okay, so we will find that the governing equation that we would have is exactly the same as whatever we were looking at earlier. Okay, so this is the only viscous diffusion term which is going to survive. The other one, which is a second derivative of u with respect to x, is going to go to 0 because of this condition, and the inertial terms or the advection terms on the left hand side are also 0. I mean, because v is equal to 0 and dou u dou x is equal to 0 in this case. So this is the governing equation that we have, which needs to be solved. And this equation we have already encountered before. Where did we encounter this equation? Suddenly started plate, or even a vibrating oscillating plate. Both these two things, this scenario. So it's the same scenario. Okay, and you can say that instead of having a plate here or a solid thing, we have removed that plate, but we are still thinking that there are fluid which is there, and now we are not just looking at one side of the plate, we are looking at both the sides of the plate. Okay, so that's the sort of the scenario that you are looking at now. Okay, first of all, problem statement clear, everybody? At the interface, yes, at time t is equal to 0, that's right. So if I were to plot, for example, this is my y direction, this is my y, and this is my velocity u, then I have at time t is equal to 0, this is how the velocity varies. So this is plus u and this is minus u, and this is how the velocity is. So this is only at time t is equal to 0. After that, this gradient will not exist. Okay, so at time t is equal to 0, we create the situation, we leave it, and then we will see how the solution is going to evolve, and that is exactly of our interest to us. Okay, so you can think of that there are fluids which are moving in the two directions, two sides. Suddenly I remove the plate. Okay, so now the fluids are still moving in the same opposite directions. Okay, and we would now like to see how exactly this diffusion is going to happen. So again, how to do this experiment? Okay, it's not that straightforward. These are always tricky experiments because you'll have to think about what you are doing. But in principle, one can set it up. Okay, and in principle, one may not have an infinite thing, but then we can say that, okay, maybe there's a region where this condition that the end effects or end conditions are not very important can be met. So those are like, most of the time it is possible to sort of meet the in an approximate sense, a reasonably good sense, it is possible to set it up. So the boundary conditions that we are going to use are u at y and all 0 time t is equal to 0. Maybe you can just write it as t is equal to 0 and all y was, you can just say, I will just put it as capital U times sine of y. This is just sine function. So this is equal to plus 1. It takes the sign of y. All it is saying, it takes the sign of y. So if y is positive, it is positive. If y is negative, it is negative. That's as simple as that. And so this is my initial condition that I have. My boundary conditions are, so we can go to infinity, we can use the boundedness condition, or here, I mean, so we can just say it's bounded, velocity is bounded. At infinity, plus minus infinity both. So you can say that u at all time y tending to plus infinity is equal to bounded. And similarly, t y tends to minus infinity again is bounded. So as we know, this equation needs one initial condition and two boundary conditions for its complete solution. And these are the boundary conditions that one can prescribe. We have already said that there are no natural length scales or time scales in this problem. So that means that one can look for a similarity solution. And similarity variable we have already introduced earlier, same similarity variable. In fact, very similar. So in some sense, it is very similar to a suddenly starting plate problem. Okay, suddenly starting plate was at time t is equal to 0, suddenly you started the plate. Here you are saying that the gradient already existed, okay, at time t is equal to 0 because of the positively directed motions. And then that's why you would like to see what happens now. So introduce a similarity variable as before. We are again going to have eta, and this eta is equal to y upon square root of nu t. Remember that this was our similarity variable, right? And we had used a 2 in there along with that for simplicity. So same similarity variable is what is going to be used here as well. So what is the next step now after having introduced the similarity variable? Is to transform the governing equation. So this is one exercise I would like you to do. Okay, in the next homework, please this is add to this problem. Homework what, 7 now or 6 now? Maybe 7, right? So whatever is the latest homework, add this. So transform the above equation. So that you are not just saying it in the class, you actually go back and do it for yourself once, at least once, so that you are confident that you can get this equation. So the equation that transform the above equation and get d to f d eta 2 plus eta square to eta df d eta is equal to 0. Okay, so that's the that's how the governing equation can be transformed to. So again, we are starting from Navier-Stokes. Okay, we have shown exactly that the equation will reduce to this form, and then we are saying that we are using similarity of variable, which is given here, and introducing a function f. Okay, and so f was like u by this velocity capital U, where this is some function of eta. So u is now a function of eta divided by, so this is now a function of eta. So these are exactly the same as whatever we had done earlier. We're not really changing anything as such here. So we get, so if we solve this and we get, so you transform the boundary, the initial conditions and the boundary conditions. So after transformation, you will get the, again, the same issue that we have talked about earlier. A PDE, which required 3 conditions, is now changed to an ODE, which requires only 2 conditions. Okay, and therefore 2 conditions, or 2 of those conditions should merge with each other, which they do. And so here, in fact, instead of bounded, we just use the condition, this is capital U and this is minus U. Bounded should be good, but maybe in this case it is more convenient to just say that it is bounded and equal to capital U and minus U depending on where you are. So my boundary conditions will become F as eta tends to plus infinity as 1 and F as eta tends to minus infinity as minus 1, as minus 1. Okay, and I can solve this equation again, like whatever we had done. Again, we had gotten an error function earlier, we will get an error function again here as well. And my solution is U is equal to capital U, error function of eta, and eta is U error function of y upon 2 times square root of nu t. Okay, any questions here? So this actually falls along very similar lines to whatever we had seen earlier for a suddenly started plate. Okay, it's a very similar solution. Okay, it's just a small difference in interpretation that has to happen, which we will do in a minute. Okay, so earlier I think it was 1 minus error function. Now here we have just error function. Is the change has because of the boundary conditions that we are now putting in. Okay, so the boundary condition changes in the boundary condition, but otherwise you will see that it has a very similar form that that is still there. Okay, any questions here now? So if you were to plot this solution, so maybe you can say that this is what I have at time t is equal to 0, and as was mentioned that I cannot, how can the solution exist? But this is, as we said, is only an initial condition. We are not saying that this is how the solution will turn out to be. Now what is telling us that the solution will turn out to be, let us say if this is my axis now, just like we have axis here, it will become something like this. So very so it will essentially asymptote to 1 or capital U here. It will also asymptote to minus U here. So these parts, so that essentially what we are saying is that after some time it will essentially become something like this. This is my error function, and this is how the solution will start looking like. So it will asymptote to both these two values at very long, so very far away, you can say that the flow has does not know that the plate, that the plate has been removed, the interface is now there, has been created, where because of which earlier, it was absolutely fine. It was just like uniform flow on this direction, uniform flow on the other direction. There was nothing that the flow had to readjust itself. But the moment after you have removed this, the separating plate, and you have exposed the two fluids to each other, then we know that there will be a diffusion of momentum which is going to happen from this. So this stream will try to move less on the positive side, and this will start to move less on the negative side, which is what this graph is telling us. Okay. Everybody clear? Physically, we understand the solution, understand the problem and the solution, and of course the intermittent steps in between, how we obtain the solution. So now the next question arises. This is something that was there in the midsem. I have already graded the midsem, so we will be looking at the copies tomorrow. Okay, so that's another reason for you not to make not to miss tomorrow's class. Now, the question that was asked when we were looking at a solution like this, what is the width of the diffusion? So you can see that this is the part, after some part, the flow is as good as unchanged. Okay. So what is this width? What is this region which sees the presence of that these things have been changed here at the interface? Okay, so that's what we are looking at, interested in looking at. And it is very clear that with time, this region will only grow. Right? That is sort of physically clear that it is going to grow with time. We are interested in just finding out how does it grow. So there, how do we look at it? So we say that the point, so we have to define a point which is somewhere here. So we are going to say that the velocity becomes not u. So u, this solution will asymptote, so it will never reach u, or it can only reach asymptotically, that means at infinity. But let us say, so I will define some sort of a cutoff. Let us say I say it is 0.95 u. So when does the velocity become at what? If I draw a parallel line at 0.95 u, then this is going to intersect this curve somewhere, and that is what I would look at it and say that this is my thickness, this is my delta. This is the thickness over which the diffusion has happened. Okay, and it's very clear that because it is symmetric, whatever is happening on the top will happen on the bottom side. Okay, so this 0.95 u is an arbitrary number. This is 5% of the maximum velocity that I would have. Okay, so it's like that's how I have defined this. I can make it as 98%, 99%. These are some other criteria that people use. 95% is more useful, just because uncertainty in measurement could be like 2%, 3%. So 0.99, differentiating between 0.99 and 1 is very difficult because the uncertainty itself is like 2%. Okay, whereas if 0.95 and 1 is much easier to differentiate because again it is beyond my experimental uncertainty. I should be able to pin that point more precisely. Okay, so that's the simple consideration. Okay, so that's why people use that. If your measurements are too noisy, you can go with 0.9. Okay, which is not a very good measure, but I mean, if nothing else, you can use that. So here, what we said, again, we are looking at the error function. This error function takes a value of, so what we are saying now, so I think this part was not clear to a lot of people, is what I can understand, or I could figure out from the solution that was given. So this is what we are doing. So we are just rewriting it in this form, and we are saying this is now 0.95. Okay. So now 0.95, the error function now, although it is not possible to directly invert this, we can, let us say, go to a table or a graph and see where does error function the value of error function becomes 0.95. That's what we are saying. So where does it become? So eta, it becomes at eta. So this becomes, gives eta is equal to 1.38. So this is a value that I read from the table, or if you can calculate the error function, you can calculate it at the various points, and you will find that at 1.38, this has a value very close to or almost exactly equal to 0.95. Okay, so that is basically the eta value that I take. So now what is my eta? Eta is nothing but, so that means that this quantity now, y upon, so eta is equal to y upon 2 times the square root of nu t is equal to 1.38, where for u by capital U is equal to 0.95. Understood? Okay, so this is an important point. I think people have sort of I'm not sure a lot of people have missed it, so therefore we are just redoing it. Okay, and that means that, and this, when velocity becomes 0.95, we are calling it as delta. So you can say now I can put y is equal to delta. So delta is equal to now is equal to, so y essentially has become delta, is equal to 2 times square root of nu t times 1.38. So this is now I'm using this part of the equation and saying that this is what I get as delta. So my delta becomes, in the previous problem, was 2.76 times square root of nu t. Okay, in this case, it is going to become twice of this. So in our case, present case, this is going to become twice of this. Okay, because we have delta on both the sides, so then this will become multiplied by 2, 5.52 times the square root of nu t is what I will get here. Okay, because the diffusion is happening on both the sides with a width of 2.76 nu t, square root of nu t, and therefore it is 5.52 times the square root of nu t. Okay, and it again, so this is what tells you that how does the diffusion change with time? It increases as square root of time. And we said that this is a typical behavior for diffusion process. Diffusion happens as a square root of time, t to the power of half. So if you are looking at a problem phenomena, you don't know where, how does, I mean, whether it is diffusion dominant or something, one way is to look at the characteristic and see whether it is changing as t to the power of 0.5 or close to that. If you find it close to that, then you can say it is primarily diffusion dominated. Okay, and that's why we keep doing this problem. It's a very fundamental problem, as we said, somewhat theoretical, difficult to set up, and so on. Okay, but it is useful because it gives us in a very, very nice, neat way to explain how exactly the diffusion thickness is going to vary with time. This constant is, of course, important to finding out the thickness, but of course, this is dependent on the arbitrariness which is here. This is an arbitrary thickness, by the way. Okay, so those people who have actually looked at it as 0.99 and so many other measures, we have still given you quite some marks for that, because this parameter is not important, but ultimately trying to do this part is what is important or clearly needs to be understood and explained. Okay. Now, the other second part of the question midsem was to look at viscosity was changed by a factor of 100. So that changes. So you can see that the solution, the thickness depends on both the viscosity as well as the density of the fluid, because both these two parameters are here in this new parameter. Okay, so if I change either viscosity, if I change the density, either of them, this delta would change. So in the other case, my viscosity was increased by a factor of 100, and these numbers were chosen so that you don't have to use a calculator. So you can see that delta will increase by a factor of 10. Okay, because the square root dependence on u is what you are getting here. So that means that in the first case, if it has a certain thickness, the second case when it is CMC has added or the viscosity is being increased by a factor of 100, then the diffusion thickness would be 10 times of whatever you were finding earlier, right? So is this clear now? So again, this calculation of the length scale. So what is important here is that this does not allow you to find out the length scale. Okay, so we are defining a length scale by going to the velocity and saying that where does the velocity become a certain percentage of whatever is the characteristic velocity. Same idea we have seen earlier, we are seeing here, as well as when we go to boundary layers, we will see the same idea. Okay, because we don't have a natural length scale. So we define it using the velocity scale, and that's why essentially this is the steps that we are doing here. So I'm just going to pause here for a minute and make sure that you've understood how exactly we are doing this. So again, I'm just explaining it once more. So this is the velocity I get. Okay, I put it as u by u is 0.95. Okay, and then I look at what is the value of corresponding value of eta that I have. I get eta is 1.38. Now I say eta is not, this is my definition of eta, this has to be 1.38. Okay, and therefore this is my y I should get, but that y I'm already calling it as delta. So I replace y with delta. Okay, and I get delta as 2.76 times the square root of nu t. That's essentially what we have done here. And here we are saying it is diffusion is happening on both the sides, so we multiplied by a factor of 2. Okay. So now the next thing, in this case, maybe we would want to do, and as we said, okay, just transform this equation once, okay, from the governing equation that we had, which was a PDE, to this ODE, okay, and do it as part of this homework. The next homework that you are going to submit, add that one question to your list, and you have to submit it because so that we know that you know how to transform these equations. This is a reasonably simple equation. Once you know if you can do this, you should be able to transform others if you encounter them in the future. So, so once we have a solution, we can find out what is my vorticity. So vorticity in this case is simply dou y minus the minus sign plus dou v dou x. Okay, and which will give me that, because I already have my u expression for u, I should be able to differentiate this with respect to y. Okay, so what is the derivative of error function? Okay, think of it the other way around. What was an integral of? It was an integral of e minus eta square, which was a Gaussian function. So from Gaussian function, by integrating, you got to an error function. So that means that if you start with the error function and differentiate that, you will get a Gaussian function. Okay, so that's what you get. So you get it as, if you do this correctly, you will get an expression like this, upon pi times the square root of t square root exponential of minus y square upon 4 mu t. So this is my omega, is what I will get now. So now if I look at the this function, what does it tell me? If I look at the width of the function, so you can see that first of all, this function is centered where? The Gaussian function, right? This is my Gaussian function. Okay, so this is my x. Let us say, if I'm looking at it in terms of, let us say y, if it is this to y, then this is my exponential of minus y square. Exponential of minus y square, if you look at, this is how this would look at. So at y is equal to 0, this has a maximum value, which is equal to 1. Okay, and as y tends to infinity, it becomes 0, y becomes minus infinity, again it becomes 0. Okay, because it is a minus y square. Exponential of minus y square. So, so there are two parameters which define it, where it is centered and what is this width. I can have a Gaussian which looks like this. Okay, or I can have a wider Gaussian. Both of them are Gaussian functions. The only difference is that there is a width here, so I can define some sort of a width parameter, exponential of minus y square upon some width here, b. Okay, so by changing the value, earlier case we had taken the value of 1 implicitly, now we are not saying it is 1, it could be anything that I can put in here. So by changing the value of b, I can adjust how fast it goes to 0. At y is equal to 0, this b parameter does not do anything because the function is anyway 1, but how fast it goes to 0 is now by taking y tending to infinity is what is being controlled by this parameter b. So if I look at this function, okay, so you can see that the width of this function, of this Gaussian, this is a Gaussian function, okay, and of course I can also put amplitude to that. Let us say I put an amplitude capital A multiplied by A. Then what will happen is at y is equal to 0, it will no longer go to 1, it will go to A. The value will become A. So that means that the whole curve is now shifting up and down, okay, because or getting multiplied by, and because it is getting multiplied by parameter A. Okay, understood? This is how we look at a Gaussian function. So in this case, the Gaussian function, you can see that the width of the Gaussian function, how does the width of the Gaussian function change with time? So as we have said here, what is happening is that you will have this curve at some time. Okay, let us say at earlier time you had this curve. Okay, so this is at time t is equal to 0. This is at time t is equal to t1. This is at time t is equal to t2. So this is how time progresses, and you will move. You will that information will diffuse to a larger distance, right? So that is understood. Now, what is happening to my vorticity, which is what we have calculated? The calculation is there, okay, but we are just trying to understand it physically. So physically, what is happening now? That with time, the width of the Gaussian has to increase. That is clear. Okay, it is diffusing fast, which is, so my width here, if I just compare, my b square in this case is equal to 4 times nu t. Okay, so my width of the Gaussian is essentially equal to 4 times the square root of 4 nu t. So again, you can see that there is a square root of nu t behavior. So the width of the Gaussian is increasing as square root of t. Okay, and my amplitude, what is happening to my amplitude? You can see amplitude is dependent on time. Okay, so my amplitude is reducing with the square root of t. Okay, so my width is increasing as a function, as a square root of t, but my amplitude is reducing by a factor of square root of t. So what do you expect the integral to happen? The total vorticity is conserved. Okay, so if you were to find out omega dy integral of this from minus infinity to plus infinity, this is my total vorticity that I have in the domain. So we can leave out a few of these things for yourself. Maybe it's a good idea for you to go back and redo these things. Okay, so you should be able to show that this becomes equal to 2u, which is constant, independent. So this will show that this is, so this is again, let us put this as a small exercise, show that this is what you would get, where this is, you can say this is independent of time. Note so at time t is equal to 0, it is very clear that du dy was 2u, right? Okay, in fact, in some sense it is infinite, but if you just take any length scale, it is like 2u, that is what you have, and that is what you have throughout. Okay, that's what you would have throughout. Okay, so this is the first problem that you would like to do. Any questions here? Why do you say that? Vorticity is just, we have defined it as omega dot curl of velocity, right? So I can take the curl of velocity at any point and I can find out. So when we said that at a line, we said that we want to idealize that because we don't want to, when we look at interaction of vortices, having a finite size core makes it difficult for me to analyze. Okay, so I lump all the vorticity in a given line. Okay, so I don't have to worry about the finite size, because then you can say, oh, this finite region, what is now happening to that? Because earlier, so here, okay, so we said that there is one vortex here, let us say, then there is, there's another vortex here, there is some rotation, and we say that, okay, how much is the vorticity, how much is this velocity getting induced at the other point, right? And this was a very simple interaction. That's how we started to look at the interaction, and I have given you one interesting problem of leapfrogging of vortices in the homework to look at yourself, okay, and see how there you will have to look at not just 2 vortices, but maybe 4 vortices and do the analysis that way, or 3 other vortices, because there is a 4 vortices is what you have in the domain. So at any given point of time, we will have to look at the effect of 3 other vortices that they will be doing at your point. Now here, if instead of this, you think of that there is a finite size vortices. Okay, now what is going to happen? Okay, you will have to say, okay, this is going to move in this direction, but this, what about this point? What about this point? Okay, so this is what is being induced, and then there is a velocity which was there. You have to add up the two things, and becomes unnecessarily complicated. Okay, so it's like an idealization. From here, we just said that, okay, let us neglect the core, neglect vortex core, and let us just go here. So this is only an idealization. So line vortex, as we said, kept on saying that, okay, we are just thinking vorticity is shrinking to a point because the distance at which we are looking at is very large as compared to the size of the vortex. Okay. But of course, nothing is concentrated at a point, at a line. It is only an idealization for the sake of, again, simplicity. And the same thing now we are going to look at is how does this line vortex decay with time? So the next problem, exact solution that we are going to look at is decay of a line vortex. So we have already said that there is a vortex, line vortex, which is here. Think of that this is going, it's an infinite line, it's just spinning, rotating in certain direction. Okay, we know that the velocity that it will induce is, let us say if this has a strength of gamma, then the velocity everywhere is gamma upon 2 pi r. That is my u theta. Right, we have already seen this enough number of times by now. So now what we are saying is, what do we mean by decay of a line vortex? We are saying at time t is equal to 0. I mean, earlier it was spinning, everything was, this was already set up, the flow field was already set up. Now suddenly I stop this vortex. Okay, so it's like it was rotating, I just put my finger here. Okay, and therefore now there is no more rotation of this which is happening. Now I would like to see how the velocity around it is now going to change with time. Okay, so there is an axisymmetry, etc., which is there. So you can simplify the governing equation, and you would get the governing equation. Simplify the Navier-Stokes equation and get dou u theta dou t is equal to nu times dou by dou r, or 1 by r dou by dou r of r u theta. So this is my governing equation. This is from the theta momentum equation. These are the two terms that will survive, and nothing else will be there. There was no ur anyways. There was only u theta. So in fact, we have already sort of seen a simplification of that. Okay, the only term that essentially gets added here is the unsteady term. Earlier, this part was also not there, and we had solved this part, but now the unsteady term will get added. Same set of arguments is what you can go through. So again, we'll need 3 conditions, 1 initial condition and 2 boundary conditions to solve this problem. So we can say that this is subject to u theta at t is equal to 0 and or r. What was the velocity? What is it? What is the initial condition I should prescribe here? At time t is equal to 0, everything was just spinning as if nothing had happened, right? So it's gamma by 2 pi r. Now at u theta, what happens at 0? R is equal to 0 and time t. U theta, I have said that I have made it as 0. So in some sense, earlier it was infinity. We have already seen why it is. There is a singularity at r is equal to 0. Okay, this term function, as you can see, becomes infinite, or in undefined, unbounded, grows unbounded as r tends to 0. Okay, but now we are saying it is now stopped. It is now going to 0. Velocity has become 0 here. And then u theta at or times t, r tends to infinity. Let us say is still gamma upon 2 pi r. Okay, so very far away, the flow does not know that it has stopped, that the center things have stopped. So it is, of course, as r tends to infinity is still 0 anyways, but we just say that this has this behavior as 2 pi r, 1 upon r sort of a dependence. Okay, so so this is the problem statement that we need to solve. Everybody clear about what is the physical problem that we are solving? And then the governing equation. Okay, we have not derived it, but we said that it's a very similar again to whatever we had seen earlier. Then the conditions, we have not explicitly written it down as initial and boundary condition, we just said subject to, it's the same thing. So the conditions, boundary conditions in initial conditions clear, right? So the problem statement is very clear as to what is happening now. So how will we start solving it? First step, in this case, look for a similarity solution. By now it is very sort of, we have already said it so many times, so we are going to look for a similarity solution. Why similarity solution? Because there is no natural time scale, length scale in the problem. Okay, it's not that after time t is equal to, after certain time t1, I do something else and etc. If I do that, then my similarity solution will not apply. Okay, in this case, I'm not doing that, so I don't expect anything to bother me. So I can look for a similarity solution. And what will tell me if the similarity applies or not is that these three conditions will, hopefully my governing equation will reduce. Ultimately, in similarity, what are we trying to do now? Again, philosophically, what is it that we're trying to do? Once more, I will tell you. Yes, we are reducing the number of independent variables. So we are saying right now u theta is a function of r and time t. So instead of doing that, we are looking for something which is u theta now which is some combination of these two things. Okay, so it is some other parameter which we call it as eta in this case again. So eta is some function of these two things. So which is equal to, in this case, is r square upon 4 nu t. It's the same, again, same parameter as what you can get here. Working with a square rather than a square root is more convenient. So we will work with this parameter. It's the same parameter as y upon square root of nu t. Okay. And we are going to look for u prime, which is equal to u theta upon some velocity scale. Now you can see that gamma upon 2 pi r looks like a lateral velocity scale, gamma upon 2 pi r. So if I normalize u theta by gamma by 2 pi r, then I get this as some function of eta. Okay. So what we are saying is that instead of saying u theta, which is a function of r and t, you are now saying u theta is only a function of eta, which is some combination of r and t, but provided that we normalize it in this manner. So it is essentially u theta is gamma by 2 pi r times a function of eta, which is nothing but what has been given here. So what is the next step? So once you have found the similarity variable, what is the next step? We have done it now. We are doing it third time or maybe the fourth time. Transform the governing equation. GE governing equation, and I get f double prime or d2f d eta 2 plus simply df d eta is equal to 0. Okay, so this is what you would get. The governing equation will transform to. Just remember that why are we getting different things here? when we are starting off with apparently everything the same, is because there are subtle differences in how we have written our similarity variable. There are subtle differences in the governing equation that we have. Okay, so both these two things will change this equation that we are going to see after transforming. Okay. So now what are the boundary conditions? This is subject to that my f infinity is equal to 1 and f0 is also 1. So I need two conditions, and then these are the two conditions that I would have. Now with this, if you were to solve it, in fact it should be 0. In fact, f0 should be 0. Yeah. So solve to get, now this is a very simple looking equation, right? Constant coefficient type of ODE, readily exponential of whatever, lambda, eta, whatever is the variable is what you can choose, and you can very easily get a solution for this. So you get, in this case, exponential solution, solve, and we get f eta is equal to 1 minus exponential of minus eta. So that's all the solution is, okay, which will satisfy these two boundary conditions. As you can see that as eta tends to infinity, this term becomes 0 and my solution goes to 1. And when eta is equal to 0, then this becomes 1 and 1 minus 1 is 0. So this satisfies both these two conditions. Okay, and it does satisfy the governing equation. You can substitute that and you can verify that it does satisfy your. Anyway, one satisfies it because both of them are differential, and here it will get, yeah, just put it and you'll see that. Okay. So what is my u theta now? So u theta is equal to gamma upon 2 pi r. So you can see I'm coming from here, gamma by 2 pi r. U theta is gamma by 2 pi r times this function here. Okay, this function is 1 minus exponential of 1 minus exponential of minus eta, and eta is nothing but here. So 1 minus exponential of minus, okay, just write it in the same line. U theta is equal to gamma upon 2 pi r, 1 minus exponential of, let me just write exp, minus r square upon 4 nu t. So now what does it mean? So this is a solution that you have. So this is how the velocity decays with time. Okay, so as at very large time, what is going to happen? When t becomes very large, then this term is becoming, is going to become 0, right? So t becomes very large, this term is becoming 0. So the essentially exponential term is becoming 1. And then 1 minus 1 is 0. So essentially we get velocity becoming 0 everywhere, which is what we expect to get. So if I stop the vortex, after some time, everything will stop. Okay, which is what this is telling me. And of course, in between, what happens is what you can find out. So if you were to plot in between the, so if you were to plot for this vortex, this is my r, this is my u theta. So at time t is equal to 0, time t is equal to 0, this is what we had. And after, suddenly after some times, after time, you will have a behavior like this. So very far away, as we have seen, that very far away is still gamma by 2 pi r. So it will satisfy this condition, and later on, the velocity will keep on decaying. This is at time t1, this is at time t2. Okay, so what has changed here is suddenly earlier, I mean, t is equal to 0, suddenly at u becoming infinite, you have put it as 0, and that is what has caused this decay in velocity to be now there. So the velocity can no longer sustain itself as 2 pi u gamma by 2 pi r. The velocity will start changing itself, and it will change itself like in this manner here. And of course, again, this information will go out further with time, propagate further out with time, and more regions will start slowing down, which is what this curve is showing. So initially at this part, this much is here, and then after some time, the velocity is here. After some other time, the velocity is further down. Okay, at the same location, velocity is reducing with time. Now here you can look for solid body rotation. Okay. Okay, so there initially there will be some sort of a solid body rotation, and then this is more like a real vortex. Now, if you want to say this is somewhat like a real vortex, maybe you can think of it like that. I don't know, but of course, this is now changing with time, and a real vortex can still maintain its identity and not change with time. So that would be difference, but I mean something like what you can say. I mean a real vortex does something like this here, right? Okay, so I think we have spent a lot of time on vorticity and exact solution as we had sort of anticipated. We have done both these two topics, four lectures post midsem. And then in the next class, we'll come back and we'll start off with a new topic, which will be approximations in fluid mechanics. So what is the difference between what we have been doing now and what we are going to do next is till now we said that, okay, we could show analytically that these terms can be removed, okay, are getting removed, and the equation is getting simplified. And because of this simplification, we are able to obtain analytical solution, just like what we can see, just like two boards, we can have the solution, or maybe some more work, and we can get, because the intermittent steps are not shown here, not too much, it's like 2 pages and you have a solution. Okay, but it is not possible. It's only the Navier-Stokes can only be solved for very few cases. Some of them we have already seen here. But what about other cases? So in other cases, we will start looking at approximations. Okay, so how do I make that approximation is what we will discuss. So we will have to non-dimensionalize our equation. So we will get into the concept of non-dimensionalizing. So once we non-dimensionalize, we will see, we can compare the magnitude of various terms. We will see some non-dimensional numbers will start showing up and so on. And that will help us identify the terms which are of small magnitude, and therefore they can be removed. So you can see that removing them is only good. It's not like exactly correct, but we can remove them because they are reasonably small. So that is why we start calling them as an approximation rather than an exact reduction of the Navier-Stokes. Okay, so that's why. That's the topic that will start off from the next class, which is tomorrow, 9:30. We will meet. I will let you know the venue. Okay, so thank you.